Day 7 of AP Review, where we look at 1D motion. Alright, so position, velocity, acceleration functions. Recall that the position function, okay, if not given to you, can be attained by using separation of variables to solve the equation v equals dx over dt with an initial condition x at t equals 0 equals x naught. The velocity function can be obtained from the position function via differentiation, rate of change, aka the velocity function is the rate of change of position. It can also be obtained from the acceleration function by using separation of variables to solve v equals d over dt with the initial condition v naught, or v at t equals 0 equals v naught. Please recall that if you're asked for instantaneous velocity, that's obtained via differentiation, whereas it asks for average rate of, whereas if it asks for your average velocity, that's either found by the average rate of change of your position function or by applying the average value of a function equation to v. Okay? The acceleration function can be attained from the velocity function via differentiation. Again, acceleration is the rate of change of velocity. Again, if we're asked for the average value of the acceleration function, we can find that from the average rate of change of velocity or from the average value of a function equation applied to the acceleration function. Whereas if it asks for instantaneous acceleration or acceleration at a specific time, that's where we use differentiation. Again, velocity is the derivative of position, whereas acceleration is the derivative of velocity or the second derivative of position. Okay? Again, we apply separation of variables to find v of t, and we apply separation of variables to find r of t, provided a of t to find v of t, or provide v of t to find r of t. And it works in that order going in reverse. Displacement versus distance. Okay? Recall that displacement is the change in position of a particle over a certain time interval. More succinctly, it measures how far a particle ends up from its original position, and thus direction matters. Displacement is the integral of our velocity function from some time t equals a to some later time t equals b. The final position can be obtained by adding the initial position to the displacement. Okay? Again, the idea being is initial plus change or plus displacement gives you final. The distance measures the length of the path traveled by the particle. This length is path independent. Or excuse me, this length is path dependent, better said, because it depends on the path that we take. AKA the green path is longer than the blue path, which is, and then the red path is obviously a different length from the green and blue path. The distance is given, since the distance does not depend on the direction, okay, it's given by the integral from t equals a to t equals b of our speed function. Again, speed is just the absolute value of our velocity function. And then again, that just brings us to velocity versus speed. Velocity measures the rate of change of position of a particle, aka the rate of change with respect to time. So average velocity is the average rate of change of the position function, or the average value of the velocity function, like we've talked about in a prior slide. Instantaneous velocity is the derivative of the position function at a specific time. Okay, so if it asks you for the velocity at a specific time, you're going to use the derivative of the position function. Velocity depends on direction, so it can be positive, up or right, or negative, down or left. Speed is the rate at which distance changes. It does not depend on the direction of the particle, so it is obtained as the absolute value of the velocity function, absolute value of v of t. Speeding up, slowing down, or constant speed. Here are our conditions. Speeding up, slowing down, and constant speed are dependent on the relative signs of velocity acceleration functions. If v of t and a of t have the same sign, the acceleration acts as a pulse that causes the speed to increase. Again, it's like you're pressing down on the accelerometer or pressing down on the gas pedal of a car, and thus acceleration is in the same direction of your velocity. If v of t and a of t have opposite signs, the acceleration acts as an inhibitor. That should be an and there. That's my OCD with the grammar kicking in. That causes the speed to decrease. Again, that the idea being is that when your speed's decreasing, you're hitting the brake on the car, and hence acceleration is going in the opposite direction of your velocity. If a of t equals 0, there is no change in neither speed nor velocity, so both quantities are constant at that specific time. Direction of particle / farthest from the origin. To determine when the particle changes directions, apply the first derivative test. Locate the critical points of x of t, aka where is your velocity equal to 0 at. We do not have to worry about velocity not existing because we assume velocity is continuous since we're always going to have some velocity at some time t. Determine the sign of the velocity in between the critical points. interpret the direction of the particle from the sign. Okay, so this is for when we're determining when our particle changes directions. If we want to determine when the particle is farthest in a certain direction, we locate the critical points, but instead of applying the first derivative test to our velocity function, we apply the candidates test to the critical points and endpoints of our interval. We evaluate x of t at the critical points and the endpoints to determine where x of t obtains its maximum and minimum values on the interval. So example as a position versus time graph, okay? We can see right here for a position versus time graph, we are slowing down from 0 to 2 because we can see that, that our velocity is negative here, aka velocity slope of the position versus time graph, but our acceleration is positive because we're concave up in this region. Likewise, we're slowing down from 4 to 5 because we can see that our velocity is positive here, but that we're concave down, which indicates a negative acceleration. From 9 to, and then we see that we have that corresponding reasons from 9 to 10, and then 11 to 12, okay? AKA slowing down is where our slope becomes less and less steep as time goes on. Speeding up occurs from 2 to 4 and 7 to 9, okay? Because we can see from 2 to 4 that our velocity is, our slope slash velocity is positive, and our acceleration is also positive as we're concave up, aka our slope is getting steeper and steeper and steeper. From 7 to 9, we see the same thing happening. We're speeding up in the negative direction because our slope is negative, our velocity is negative, but we see that we are concave down in this region, so our acceleration is also negative. We see we have a change in direction at t equals 2, 6, and 10, because that's where we have our change in velocity vector, or change in velocity signs. We go from negative to positive at t equals 2. We go from positive to negative at t equals 6, and then at 10 we go from negative to positive again. We're stationary, aka we have zero velocity from the interval at the points t equals 2, aka our velocities can briefly be equal to 0 at t equals 2 since we have a horizontal tangent line, and the same thing at t equals 10, and then from the interval 5 to 7 right here, as we're flat, meaning our position's not changing from 5 to 7. Now, be careful because this was a position versus time graph. Now, if we look at a velocity versus time graph, okay, we are going to be slowing down from 0 to 5 because we see that our graph is moving towards the 0 meter per second start at 5 seconds, meters per second part at 5 seconds. In terms of the language of calculus, which is what you'll need to explain on the FRQ section, okay, we say that we're slowing down because our velocity is positive, but the slope of our velocity versus time graph, which is acceleration, is negative. So we have opposite signs for our velocity versus time graph. Opposite sign for velocity and opposite sign for acceleration. Now we're speeding up from 5 to 10 because our velocity is now heading away from the 0 meters per second mark. Okay? In terms of language of calculus, what's happening is that our velocity is negative. We can look at that on the y-axis. And the slope of velocity versus time graph, which is our acceleration, is also negative. So velocity and acceleration have the same signs from t equals 5 to t equals 10. We have a change in direction occurring at 5 seconds because we can see that our velocity changes signs from positive to negative at t equals 5, and our velocity is briefly 0 at t equals 5. We're stationary at t equals 5, meaning we have 0 velocity very briefly at t equals 5 seconds. And then lastly, we could say we have a constant velocity from t equals 10 to t equals 15 seconds. And that covers day 7 of the AP Calculus AV review.